Yes, no, that's right there.
Okay, let's get started. Are people still in the lab, Brittany? Are we done?
No, they're all.
They're all out? Okay, so they're making their way here probably. Okay, let's finish up spectroscopy. Today is the last lecture on spectroscopy. So we're gonna go over atomic absorption and atomic emission. You already had the lab, so you are pros. This is just going over the theory. Before we get there, let's just remember a little bit what we talked about last time. So what is Beer's law?
A equals ABC.
Yes, A equals ABC. Great. What is A and what are ABC? Do you want to go for it?
Okay, so it's
The big A.
yeah, it's the absorption.
Yes.
A is absorptivity.
Yes.
And B is the distance that it travels through, so the size of the cuvette.
Yes.
And then C is
It's the most important part. Concentration. Yes. Perfect. So A equal ABC. How wonderful is that? So it is the linear relationship basically between absorption and concentration. So if you get asked this question in an exam, you want to say it's the linear. So you want to state the equation and state what the ABC are, and then it's the linear relationship between absorption and concentration. Why absorbed light is not equal incident beam minus transmitted light. So you have the incident beam that hits the sample or the cuvette, what have you, and then you have the transmitted beam or the exiting light. Why this minus that is not equal the absorbed light? Let's go with Medora.
Because some of the light can have been like diffracted or scattered.
Absolutely. So light can be reflected. So it hits the cuvette. Part of it can be reflected like a mirror. And then some of it gets scattered. Some of it actually gets absorbed by different constituents that you don't care for. So these are the interferences. So scattering of light, reflection of light, refraction of light. So that's all why it's not a simple subtraction. How does the monochromator function? What is a monochromator and how does it function? Jason, go back the back. Yes. Perfect. So isolation of a specific light, of a specific wavelength to be very accurate in the response. So a specific wavelength or a very narrow bandwidth of wavelength. But first of all, the light has to be diffracted. So there is a diffracting system or diffraction system inside of that unit of monochromator. So first of all, all the light gets diffracted by a diffracting or grating system or a prism or a combination of both, so that you have lights of different wavelengths, and then you have a filter that filters through that selected wavelength. So what is the importance of monochromator in terms of Beer's law? You want to go for it, Ian?
Yeah, it's based on monochromatic light. So the relationship is based on that, and because different wavelengths have different abilities.
Yes. So basically, compounds at different wavelengths have different absorptivity. Then if you have polychromatic light, you cannot relate, you have deviation basically of Beer's law. So you really need to have this select wavelength to get the absorptivity to measure absorption and relate it to concentration. Okay, Great. So moving on, atomic absorption or atomic fluorescence or emission spectroscopy can be absorbance, measuring absorbance, or you can be measuring emission. So atomic AA is atomic absorption spectroscopy and AES is atomic emission spectroscopy. In atomic absorption spectroscopy, we have flame AA, like the same as you use in the lab. And then you have the electrothermal atomic absorption spectroscopy. It's less common. We'll talk about it briefly today. And then under atomic emission, there is the flame emission spectroscopy, whereas the most advanced, and you find in most labs that focus on mineral composition, is called the ICP, or inductively coupled plasma atomic emission spectroscopy. So the abbreviation is in next slides, but ICP, atomic emission spectroscopy, is more common nowadays to measure minerals than atomic absorption. It's more efficient. It has a higher sensitivity and a lower threshold. So if you want to say you have a lot of food samples and you want to measure all of the minerals in those food samples, you send it, let's say, to Eurofin, who bought Covan's lab. They have ICP. They run ICP analysis rather than atomic absorption. We don't have ICP, but a different department in the college, the soil department, they measure minerals in soil. They have ICP. Okay, so basically in atomic spectroscopy, we care for, in food analysis, basically, we care for determining mineral nutrients. So in the lab, you determine calcium and iron. These are based, potentially are important minerals, and they are on the nutrition label. Sometimes we need to measure other than calcium and iron, potassium, sodium, also are on the nutrition label, but there are also other minerals that are of interest from a nutritional perspective, and also from toxicity perspective. So lead, for example, mercury, cadmium, nickel is another one. So this is your periodic table. We all love the periodic table. Those that are in pink are elements that we can actually determine using atomic absorption because they can be in metallic form. So we can measure those and they absorb light and they can also emit light. Okay, so again, just remembering the energy transitions in atomic absorption, since it is atom, we're measuring the absorption or emission of light of an atom, a neutral atom. This is very important. Neutral atom, not ionized, neutral atom in a gaseous state. So since it's an atom, not a molecule, so the energy is electronic energy. So the electron in the valence shell, or the valence electron in the outer shell, is hit by a specific wavelength or light at a specific wavelength, and it gets excited to a higher energy level or higher shell. And then going back to ground state, it emits a little bit of heat, and it also is going to emit light at the longer wavelength. So we can either measure the absorption or the emission of atoms. So here is just an illustration, again, reminding you that molecules and atoms can absorb at different wavelengths. So atoms in this case can absorb at different wavelengths. They also have a lambda max, and they emit light at longer wavelength because less energy, some of the energy is dissipated as heat. Also, there is an emission at maximum at a specific lambda. So Once we know the characteristics, we can set up the absorption wavelength and the emission wavelength accordingly. And here's just illustrating that you don't have rotational energy, you don't have vibrational energy, because you don't have molecules. You are measuring absorption of atoms in gaseous state. So basically the energy transitions are only electronic energy, and they have to be allowable energy levels. So that's why we select specific wavelength. So you've done this in the lab, you prepared your samples, and samples are in solution. What happened is you put the little capillary tube in your sample, and then a sample gets aspirated, pulled up, and goes into a small nodule that transform it into a mist. So it's basically the fine particulate of your samples are projected to the flame. So now you have the nebulizer, is the word I was looking for, where your sample goes through the nebulizer and becomes a mist that goes into the flame or the plasma. Once it goes into the flame or the plasma, your solvent evaporates. And not only the solvent, the carrier solvent evaporates, your elements in molecules, the bonds are broken. So if you have sodium chloride, whatever, ferric chloride, the bonds are broken, and then you have your individual elements in an atom format that is in a gaseous state. So it's very important that they are neutral atoms, because if your flame is too hot, what happens is that your atom will ionize. And once you have some of your elements in neutral atom form and others in ion form, you have different absorption. The ionized form will absorb at different wavelength than the atom form. Then you would have their lambda maxes will be different. And then if you select for lambda max for the atom and half of it is ionized, then you'll get underestimation. So when you were writing your report, or when you talked about over and underestimation, one big part of underestimation is adjusting the flame temperature. So you adjust the acetylene and the air concentration so that your flame temperature is just enough for vaporization and breaking of the bond, so you can get atoms and you don't get ionization. If it's too hot, you have a lot of, let's say, fuel, it's too hot, then you will end up going to the next level of matter, the state of matter where you have an ion instead of a gaseous neutral atom. So we don't want that. Another thing you learned in doing the lab is that you have a specific lamp for different elements. So we call these lamps that you have used in the lab the hollow cathode lamp. So you did calcium, you did iron, and you changed the lamps in between. So the lamp has neutral gas in it, mostly argon or neon. But what's important is the cathode in the lamp. The cathode is made up of the metallic form of the element of interest. So if you're doing calcium, it's going to be made up of the metallic form of calcium. If it is iron, it's going to be made up of the metallic form of iron. So basically, when the light is discharged, it carries light spectra that is unique for that element. So it gives you the wavelength that is unique for whatever the metallic form is, like calcium or iron. So that's why in the lab you have to change lamps. You went from calcium lamp to an iron lamp, or vice versa. Okay. So another type of source of radiation or signal is electrode-less discharge lamp. It's less common. Basically, it's again a hollow tube with an inner gas. You have also the element of interest in there. And however, the only difference, instead of electric current, you have radio frequency generator. That's the only difference, but it's less common in AA. In AA that you had in the lab, we had several generations of AA in the lab. Now we have a newer one. I don't have a picture of our newer one, but basically, you have a compartment where the flame is generated. You have the aspirating unit with the capillary tube that goes into your sample. Capillary tube goes into the nebulizer, into this compartment that is actually, you're correct, where the flame is. That's when your sample is in a mist form in the flame. You adjust the air and acetylene. That's an older version. We have a newer version in the lab, but you all saw it already. So air is the source of oxygen, acetylene is the fuel to generate the flame. So you have your lamp that gives you the light spectra specific for your element of interest. You have your sample, the capillary tube, nebulizer, mist into the flame. Your solvent evaporates, your minerals are in the form of atoms in gaseous state. They absorb light. And then here you have the emitted light might have different wavelengths because you didn't have the monochromator here. So multiple light of different wavelength goes in here, and then you have the transmitted light that goes into your detector. In this detector here, you have the monochromator, where you select the wavelength of interest, and then you get conversion of transmitted light to absorption, and you get the readout and applies Beer's law. If you are measuring at singular wavelength, you can apply Beer's law, and that's when what you did in the lab. You did different concentrations of your mineral, and then you constructed a standard curve, and you got the absorption, and you converted to concentration.
Pam, this is okay. So like, we only using a monochromator on the detector side because of our hollow cathodes are only emitting. We're already like emitting kind of a focused wavelength.
We are emitting multiple because your element can absorb at multiple wavelengths.
Yeah.
But then you select for the lambda max.
Okay.
Yeah. So your lamp is emitting light in different with multiple wavelengths specific for your element, but then you select later on, you select for your specific lambda max, and therefore that's what gets translated into absorption. Yeah, that's good. Yeah, good. All right, so that's basically led me to this slide where the lamp projects, give you the energy at different wavelengths, and then your elements absorb light, and then you only care for the lambda max, so you would have the monochromator that separates that one wavelength that you select for, and it goes into your detector. Atomic absorption have photomultiplier tube detector. That's what we talked about last time, where you amplify the signal. So you have, so the light hits the anode, and then electrons get projected to another anode, another one to another one, another one, and it multiplies each time, and you have a magnified signal at the end. So photomultiplier tube detector is what you want to remember that you have in your atomic absorption unit. Now, this very briefly is a different type of atomic absorption. It's not based on having a flame. You have a graphite tube. So instead of a flame, you have a tube and a platform where you put a small amount of sample, and that gets heated at really high temperature. And then your sample will evaporate, the atom in gaseous form, and the light will be projected perpendicular to that, and the same principle occurs. The only difference, first of all, it's expensive. However, it has an advantage that instead of having to prepare 50 ml sample or whatever, maybe just few microliters of samples is what you need to put in there. However, you have lower throughput. So it's really hard to open and put the sample each time. With atomic absorption, it's just a matter of removing the sample tube and putting another sample. So that's why you have higher throughput. So you just can run more samples in a shorter amount of time. So that's basically main differences, but it's less common, more expensive. You don't see it very often. Flame emission, it used to be used as flame emissions photometry is a simple unit, and it doesn't have a monochromator, it has filters, basically to filter out the light that you are interested in. And the flame in this case is the source of excitation and also the source of atomization. So oftentimes I ask you, what's the source of atomization and what's the source of ionization or excitation? Sorry. So in flame atomic absorption, what's the source of atomization? The what? The HCl? Source of atomization that breaks the molecule into atoms in the unit. Madura? The flame. So in atomic absorption, the atomization is done through the flame. The excitation is done through what? What excites your atoms? Taylor, what excites your atoms?
The light.
Light. The lamp is your source of excitation. Very good. So this is a very common question. Again, it might appear in the midterm or the final. What is the source of atomization? What's the source of excitation? In atomic absorption, it's the flame atomizes and the lamp excites. Okay, in emission, here in flame emission, the flame atomizes and the flame excites at the same time. And it's only used for elements that have low excitation energy, like sodium and potassium. They can get excited or go to excited state at low excitation energy. So the flame is able to do that. And then they emit light. And then you can measure emission. That's the thing you want to remember. In flame atomic absorption, you have two things. You have the flame and you have the lamp. In flame emission, the flame is the source of both.
Are there like trends for excitation energy across the periodic table, or is it just kind of random?
It's just random. You don't have like this, you don't go in like increasing order of energy or decreasing order of energy. Not that I'm aware of, no. Okay, so the one thing that we're going to spend a little bit more time on is the ICP, atomic emission spectroscopy. So in ICP, we didn't do lab with ICP, but it's important for you to know because if you go to industry, you might encounter ICP more than you encounter atomic absorption. So in ICP, we use plasma. What is plasma? Anybody knows what plasma is? Go ahead, Brent.
Just like superheated gas that's like
superheated gas, yes. What happens to the gas?
I want to say ionized.
Yes, you are correct. So plasma is the fourth state of matter. So basically your ionized gas. So you can use different gases to produce plasma. Argon is very common that under certain conditions, the argon gas gets ionized then it carries a lot of cations and electrons, so it becomes a lot of ions and a lot of heat is generated. Very high temperature. Very much effective for atomization as well as excitation. So in ICP, I mean, if you get a question, what's the difference between AA and ICP? In ICP, you don't have a source of light. Okay, so your plasma is the source of atomization and excitation. So here, the plasma atomizes. You don't have a risk of ionization, even though the temperature is really high, because already the argon gas has a lot of charges, cations and electrons, that will prevent your own atoms from ionization. So you don't worry about ionizing your atoms, your element atoms. So basically, plasma atomize and excites your elements will emit light, and that emitted light will be measured. Radio frequency is used, is applied to copper oil, and it's used to generate the plasma, basically. But same kind of principle where you have your sample, you have your capillary tube, you have your nebulizer to produce a mist. But instead of your mist going into the flame, it goes into the plasma. And the plasma is ignited. You have argon gas, you have a copper coil, and you have radio frequency that is applied to the argon gas to generate the plasma. Very nice looking plasma here. And then your sample will get, like I said, atomized and excited, the components, the elements, and then they emit light. They emit light at different wavelengths. So you want to select the wavelength at which you have maximum emission, therefore you get maximum sensitivity. So the emitted light goes into your detector unit, and again, you have a grading system. And in ICP, the newer, more expensive ICP, you have multiple PMTs. So you have multiple photomultiplying tube detectors. So you can measure multiple elements at the same time. So that is the unique thing about ICP, especially the more advanced units, is that you don't have to change lamps, you don't have to do one element at a time. You can simultaneously get an emission for different elements. So cheaper ICPs, which don't exist very much, have only one photomultiplier tube, so you can measure emission in sequential. So you can measure, then change the filter, not the selection of wavelength, and then measure another element, and then measure another. That doesn't exist anymore, or it's out phase. So you'll see the simultaneous PMT instruments, where you have multiple ones all in one detector. Or more advanced and more expensive is the charge injection detector. You don't have to learn the physics of that, but with the charge injection detector, you can measure infinite number of elements at the same time. So you're not limited by the number of PMTs you have in your system. So here you can see 1, 2, 3, 4, 5, 6, 7. Some detectors come with 7, with 3, with 4 PMTs. But when you have the charge injection detector, basically you do get diffraction of light, but then you can read spectra. You can get multiple elements at the same time, basically. This is just the image you find in your book, but the plasma, the temperature, you don't have to worry much about it. But this is what I was talking about, sequential PMT. You only have one PMT. And then you just set it to sequentially detect different elements, simultaneous. Then you have multiple PMPs. And then the visual spectrometer, this is the one that has the charge injection device where you actually get all of your wavelength projected to the detector, and you can measure multiple elements at the same time. So this is the most expensive, up to $90,000. You know, companies might afford that, so they might have it and they can run multiple elements simultaneously very quickly. Okay, so preparation of your sample for atomic absorption. So your sample, your elements needs to be in solution, basically. So you have to remove organic matter so that you don't have interference. Your elements are not interacting with organic matter. That's why we ash the sample. In lab, all of your samples were dry ash, where carbonic matter was incinerated. So you oxidize, burnt off all of your carbonic organic matter, so CO2, NO2, SO2, H2O, all evaporates during ashing. What you're left with in the ash is your minerals, elements. So, but you need to have them in solution. So what did you do in the lab to put them in solution? Let's see if you remember your atomic absorption lab. Ash, not Ash, sorry, Tam.
You dissolve it in HCl.
Yes, so you started off with concentrated HCl, right? So you took your little crucible with the ash in it, and you put concentrated HCl. So the acid is going to dissolve your minerals, what you care for. If you have inorganics like sand or little rocks, that won't dissolve, obviously, but your minerals will be soluble in the acid. Then you dilute your sample. You diluted your sample. Every sample was diluted based on the expectation of your mineral content, calcium or iron. So you diluted it and you brought it up to a specific volume. And then you injected or you put it in the atomic absorption for measurements. So what we use, we were very careful in the glassware we've given you. So all of the glassware that you worked with for that particular lab was acid washed. So this lab is tedious for the TAs because not only they have to ash your sample, they have to wash every glassware you use so that you don't have contamination of minerals. So all of the acid and glassware, were acid washed. So if there are any minerals in the glassware, they're washed off. So that's why it's very essential that all glassware has been washed for you, and you ran a blank. You took empty crucible, ash crucible, and you did the same thing so that your blank contains all of the reagents that you've used in your sample is in the blank, so you can correct for any potential contamination from the agents or from anything that you have used. And then you use standards. You got calcium standards and iron standards, 4 or 5 different concentrations that were in specific concentration so that you can get the linear standard curve. So it's very important to get the right concentrations of standards, and then your samples were diluted to fit somewhere in your standard curve. So we need ashing, either dry ashing or wet ashing. Wet ashing is done with concentrated acid. So during the ash analysis lecture, this will be explained more in detail, that instead of putting them in a furnace at really high temperature, 450, 500 degrees Celsius, You might have some, iron, for example, is volatile. You might have underestimation of iron when you do dry ashing. So some of you, your samples might have had underestimation of iron because of loss in the furnace. For iron determination for label, nutrition label, people use wet ashing. In wet ashing, your mineral is not lost by evaporation because the temperature is much lower than dry ashing. You just use concentrated acid and then you heat, but not as high as dry ashing, and your minerals remain in solution and you don't lose volatile elements like iron and zinc, for example, they're volatile. Okay. So we talked about calibration being important. We have to use very, very poor standards so you don't have any interferences. And then we have to figure out the concentration where you have linearity. You don't want the curve like that. And you don't want your samples to fall outside of your standard curve. Falling outside of the standard curve can cause underestimation or overestimation of your samples. So, interferences. So iron and zinc have similar lambda max. So to avoid that, you select a lambda that is not necessarily lambda max for iron. The lambda you selected for iron was not specific to this lambda max, but we selected one where you don't have interference with zinc. So this is very important to make sure that you select for a wavelength that you're not detecting two elements at the same time. Incomplete atomization. So a reason for overestimation. So let's say your flame was cold, quote unquote, cold. That means not hot enough to completely atomize your sample. So you're going to have large molecules in the flame. They're going to scatter light, and less transmitted light is going to reach the detector. Then your absorbance calculation will be overestimated. So if your flame is cold, you might get overestimation. So if I ask you an exam, reasons of overestimation and atomic absorption, a cold flame, incomplete atomization. So that could be that molecules are still in the flame, you did not atomize, you don't have those three atoms, then the molecules are going to scatter light. Less light is going to reach the detector, you're going to have an overestimation of absorption. Transport interference. So it's very important that we prepare the standard the same way we prepare the samples. So your samples were prepared in diluted HCl. The standards were prepared in 0.1 normal HCl as well. So basically, standards are prepared in the same way as your samples to make sure that you have similar components. You did something for calcium determination to break calcium pyrophosphate. What did you add to your sample? Anybody remembers?
It's like the lanthanum.
The lanthanum chloride. Very good. So the lanthanum chloride, the lanthanum chloride replaces calcium and interacts with the phosphorus, the lanthanum. Then instead of having large calcium pyrophosphate, the calcium has a tendency to form large clusters of calcium phosphate. So the lanthanum is going to displace calcium and react with phosphorus, releasing calcium and solubilizing it so that it can be volatilized. If we don't use lanthanum chloride, you're going to get underestimation of calcium. The last thing is ionization. So again, the flame that you use, you want to prevent it from ionizing, because then you will have lower absorption at the selected wavelength. So basically, you can either adjust the flame or use suppression of ionization, but usually we don't do that. We just make sure that the flame is enough to atomize, not to ionize. So this is just knowledge of how to build our flame to prevent that. So last thing here is comparing atomic absorption to ICP. So basically both, you can measure trace elements in metallic form. So they have good precision, good accuracy. Atomic absorption is the cheaper, older technique. People are familiar with it more. However, ICP now is getting more application, especially if you can afford it. If multiple element detection is something that is done routinely, so they go for ICP. And it has much lower detection limit, so it has higher sensitivity, lower threshold than atomic absorption. And the table in your textbook is just a reference. So with this, I end spectroscopy. Tell me if you have any questions for the midterm on Friday. We have a few minutes. I can answer any questions you might have. Taylor.
What is caused again by ionization of like the atom sample? Is it over or underestimation?
So underestimation, yes, because when you are ionizing your sample, then less absorbance is going to happen at the selected wavelength. Yeah, good. Ash.
Example stimulation format to the protocols where it'll have.
So if you go to Canvas, let me show you. I want to make sure you guys are using Canvas to the fullest. Where is it? Where is Canvas? Did it sign me out of Canvas? No. Try here. Okay. So if you go to the top part of Canvas, you're going to see sample quizzes and exams. There is a sample exam from last year. Please solve it. Study and solve this exam. It's not going to be the same questions, that's for sure. Not going to be the same question. But if you study and you solve this exam, and then you go back to the key, don't look at the key first, look at the key last, then you will be able to see if you're ready for the exam. It's going to be the same format, short questions. That you would need your calculator. You will probably need to do some calculations. But here's you can see that every question does not need a lot of answer, like essays, just short answers. Sometimes the question has multiple answers correct, so you will see the key longer than it should be because I would list all possible answers. What else? Questions? I focus a lot on lab. So lab questions, that's why we post the key. The key will be posted tomorrow because I think there are groups yet to submit tonight, lab report. So, you know, if you know what happens in the lab and if you know the answers to questions, you will probably be okay. Definitely theory is important as we cover it in class, but practical is a big part of the exam.
Where do you find like the limits for the claims? Proposing to study those.
Say that again.
What reference did you use to like find the dietary claims?
For the nutrition label?
Yeah.
Oh yeah, remember in that first lecture, I put a couple of slides there and I said in the fourth edition of the textbook, they have those. Unfortunately, the fifth edition removed them, but I'll make sure that the sixth edition will have them back. So, yeah, it's look in my slides and then it refers you to the fourth edition, and I think you can find the fourth edition in your library, online textbook. Yes.
I have a question about cinematography, which is better, isotype or gradient?
There is no better or worse. It depends on what you're running. In, let's say, in size exclusion chromatography, we tend to use isostatic because it does not impact the interaction with the column, because the column interaction is based on molecular weight. Often we use gradient in most other types of chromatography, because with using gradient, you can adjust the selectivity of your column. And when you adjust the selectivity, then you can have better resolution and shorter analysis time. So we talked about gradient, and remember we said increase the strength of your mobile phase. When you increase the strength of the mobile phase, that means you're helping those that interact strongly with the stationary phase to interact less strongly and leave the column in a reasonable amount of time. If you don't do gradient elution, they will elute, but it's going to take a long time, and the peaks will be very broad because they're going to have diffusion within the column. Very good. What other questions do you have? I would like you to study well for the midterm, because the quiz was brutal for all of you. I usually review after the TA grades. I review. Some of you might have seen a green color pen in your exam. That means I went back and found places to give you additional points. So I do that. I look at all the exams and quizzes before you get them back. So first, I know how you're doing. I know who's doing well. And also I try to be generous with you if I can. So study well, ask me questions as you study. You can email me. I'm on my email all the time unless I'm sleeping at night. So I can respond to you, and good luck. Come early on Friday. Come 10 minutes early if you can. We can get started. And yeah, good luck. Shouldn't be too bad.
How does